Welcome back to AI Explains Everything, the video series where we use artificial intelligence to explain complex concepts. In this episode, we'll be taking a closer look at one of the most powerful and widely used machine learning models, neural networks. So, what are neural networks? At a high level, a neural network is a type of machine learning model that is designed to mimic the structure and function of the human brain. A neural network consists of layers of interconnected nodes, or neurons, that process and transmit information. Each neuron in a neural network takes in one or more inputs, multiplies those inputs by weights, and then applies an activation function to produce an output. The output of one neuron then becomes an input for the next neuron in the next layer, and so on, until the network produces a final output. There are many different types of neural networks, but some of the most commonly used include feed-forward neural networks, convolutional neural networks, and recurrent neural networks. Each type of neural network is designed to handle different types of data and perform different tasks. Feed-forward neural networks are one of the simplest types of neural networks, and are commonly used for tasks like image classification, text analysis, and prediction. Convolutional neural networks are often used for tasks involving image and video data, while recurrent neural networks are used for tasks involving sequential data, such as text and speech. Feed-forward neural networks, also known as multi-layer perceptrons, are a type of neural network in which the information flows in one direction, from input to output, without any feedback loops. These networks are one of the simplest types of neural networks and are commonly used for tasks like image classification, text analysis, and prediction. Feed-forward neural networks consist of an input layer, one or more hidden layers, and an output layer. The input layer is responsible for taking in the data and passing it on to the hidden layers. Each neuron in the input layer corresponds to one input feature, such as a pixel in an image or a word in a sentence. The number of neurons in the input layer is determined by the size of the input data. The hidden layers are responsible for processing the input data and learning patterns and relationships within the data. Each neuron in the hidden layer takes in inputs from all the neurons in the previous layer, multiplies those inputs by weights, and applies an activation function to produce an output. The weights are learned during the training process, which involves adjusting the weights to minimize the difference between the predicted output and the actual output. The number of hidden layers and the number of neurons in each hidden layer are hyperparameters that can be tuned to optimize the performance of the network. Generally, more layers and more neurons can lead to better performance, but also require more training data and longer training times. The output layer is responsible for producing the final output of the network, which can be a classification label, a regression value, or a probability distribution. The activation function used in the output layer depends on the type of task being performed. For example, if the task is binary classification, the output layer might use a sigmoid activation function to produce a probability between 0 and 1. One common technique for improving the performance of feed-forward neural networks is to use regularization, which involves adding a penalty term to the loss function to prevent overfitting. Overfitting occurs when the network learns to perfectly fit the training data but performs poorly on new data. Regularization can help prevent overfitting by reducing the complexity of the network or adding noise to the weights. Convolutional neural networks, or CNNs, are a type of neural network that are commonly used for tasks involving image and video data. CNNs are inspired by the structure of the visual cortex in the brain, which contains neurons that respond to specific regions of the visual field. The main difference between CNNs and feed-forward neural networks is that CNNs use convolutional layers instead of fully connected layers. Convolutional layers apply a set of filters to the input data, which are designed to detect specific features, such as edges or textures. The filters are learned during the training process, and multiple filters can be used in each convolutional layer to detect different features. The output of the convolutional layer is a set of feature maps, each of which represents the response of a particular filter to the input data. Pooling layers are often used after convolutional layers to reduce the size of the feature maps and improve the efficiency of the network. Pooling involves taking a small window of the feature map and applying a pooling function, such as max pooling or average pooling, to produce a single output value. This reduces the size of the feature map while retaining the most important information. After one or more convolutional and pooling layers, the output is flattened into a one-dimensional vector and passed through one or more fully connected layers to produce the final output. The architecture of a CNN can be tuned by adjusting the number and size of the convolutional and pooling layers, as well as the number of fully connected layers. Recurrent neural networks, on the other hand, are used for tasks involving sequential data, such as text and speech. In sequential data, the order of the data points is important, and each data point is related to the previous and the next data points. To handle this sequential relationship, recurrent neural networks use a type of layer called a recurrent layer. In a recurrent layer, the output of each neuron is fed back into the layer as an input to the next time step. This allows the network to maintain an internal state, or memory, of the previous inputs and use it to inform the processing of the current input. Recurrent neural networks have been used for tasks like language modeling, machine translation, speech recognition, and music generation. However, they can be more difficult to train than other types of neural networks because of the vanishing gradient problem, which occurs when the gradients used to update the weights in the network become too small and the network stops learning. In summary, feed-forward neural networks are simple and versatile, but may not be able to handle spatial or sequential relationships in data. Convolutional neural networks are specialized for image and video data and use convolutional layers to capture spatial relationships. Recurrent neural networks are specialized for sequential data and use recurrent layers to capture temporal relationships. Each type of neural network is designed to handle different types of data and perform different tasks, and choosing the right type of network for a given task is an important part of designing an effective machine learning model. Neural networks have been used to achieve some impressive results in a variety of fields, from computer vision and speech recognition to natural language processing and robotics. However, building and training a neural network can be a complex and time-consuming process, requiring a large amount of data and careful tuning of the network's parameters. And that's it for our overview of neural networks. We've discussed the basic structure and function of a neural network, as well as some of the different types of neural networks that are commonly used. In the next episode of AI Explains Everything, we'll be diving into the world of natural language processing. Thanks for watching, and we'll see you next time.